He does. Okay. We're live. There's and Michael. And we're gonna get George on here. You can do it. Come here. Okay. He going sent.
I was like real confused on the last problem.
That's okay. There's a couple of them.
Okay.
Yeah.
Did anyone do it?
No, it's
But like,
no.
it says repeat it, but then it just shows like a whole bunch of random things.
Yeah.
Pictures. I'm like, I don't know what to do for that one.
That's pretty much what happened to me. I did this last night, and I was like, that doesn't even make sense to me. I'm going to bed.
It's just not worth it when your brain just like keeps hitting the wall.
Right?
And
Yeah.
you're just like, okay, I'm done.
That's why I feel like the moment of inertia question on the lab, I'm like, just gonna write down.
We have a test on this crap this weekend, don't we?
I don't think it's this weekend.
It's
Really?
an exam.
Oh, really?
No, it's
We finally got a 3-week break.
Really? It's been every other week, so I just
Yeah.
figured it was this week too.
I think it's next week.
Cool. Good. Reset my weekend a little bit then.
Yep.
I was expecting it to be the Saturdays. That's how it's been.
One less thing to do.
Seriously.
I feel like my chem exams and my physics exams always line up somehow.
Oh crap.
It's
They always do. Like, yeah. It's the same way with like my calculus and stuff.
I agree with that. It seems to come in waves. Like everything piles up,
Yeah.
then you kind of get a break, then everything
Yeah.
piles up from all your classes. I hate that.
They just lined up just nicely.
Yeah.
Like they can fire me. We'll get through it.
Oh, should we just start? George still isn't here. It's been 5 minutes or so.
Have you emailed and check the email?
I can try.
Yeah, if you just try the link, just make sure it works.
Yep.
Okay. Yeah, so we can just get started. Okay. So number one, the analogies exist between rotational and transitional physical qualities. Identify the rotational term, analogous, whatever. To each of the following: acceleration, all those ones. So acceleration can also be rotational acceleration or like alpha. Again, force is just torque. Mass. I got inertia. Work. Rotational work.
I just had work.
Yeah.
Translational kinetic energy is just angular kinetic energy. Linear momentum is angular momentum. Impulse is angular impulse. Yeah. Okay. Number 2. What is the angular acceleration of the 0.28 radius of tires, assuming they don't slip on the pavement? So I got 25 rads per second squared. Or negative.
I got, yeah, negative
25 radians per second squared. Yep.
Cool. How many revolutions do the tires make before coming to rest? I got 28.7. How long does the car take it to stop completely? 1.9 seconds.
There's this equation, the final angular velocity equals initial plus alpha times t. Make 0 your final, so it stops. 95 is your initial.
I just left it.
It does this way, I think. So I don't know if that's the right way or not, but how did you do it?
Or no, I did I did the distance over like the distance over time equals velocity, and just rearranged it. Yeah, I can see that being better. Honestly, use linear instead of. Yeah, so that would make more sense. I use the linear. Yeah, I think that's what I'm messing up on, and not the radial.
So are we gonna go with 3.0? You got that too, right?
Yeah.
Yeah, if you both got that, then that's.
98 minus 25t on I sleep 2.
Yeah.
Yep.
Okay. What distance does the car travel at this time? I got 50.54 meters.
I got 50.7, but 50.54 sounds good. I probably just used 2 small digits or something.
Yeah, it's just around. And then the initial velocity is 26.6 meters per second. Does the values obtained seem reasonable? Yeah.
I know.
Of course they did.
That's what we got. Okay, number 3. A ball slides up a frictionless ramp, then is rolled without stopping, and with the same initial velocity up another frictionless ramp with the same slope angle. In which case does it reach a greater height, and why? Oh, hey George. What's up? So we just started. So we're on question 3.
Okay.
We just read that one. Yeah.
Because there's no force succession.
It's a sliding down with the crap I'm talking about, so let's go with rolling.
I think it's rolling.
Rolling seems logically a lot more sense than
Yeah. Because if it slides with the same, like you're just shoving a block up. That's kind of what I thought of it. And then if you rolled it up, then the rolling is going to have a greater distance that it rolls.
The only thing that kind of got me a little bit is the frictionless ramp. So I mean, if there's no friction on it, if it's sliding, there's no friction slowing it down.
Yeah.
So I guess that's about it. So yeah, it's just do rolling. That's good.
Okay. Number 4. Consider the 12-kilogram motorcycle wheel shown in the figure. So it is approximately an annual ring with an inner radius of 0.28 and an outer radius of 0.33. The motorcycle is on the center stand so the wheel can spin freely. If the drive chain exerts a force of 2,200 newtons at a radius of 5 centimeters, what is the angular acceleration of the wheel? So I got 555 rads per second squared.
I got 97.9.
That's what I got. What she said.
This one I was like,
I just used the moment of inertia equation and plugged in those values. Yeah, that's 1/2 times 12 turns 0.28 squared, which is 0.330 squared. And then I'll take that. You do the 2200 times 5 times 10 to the -2 for your conversion. And then divide that by the inertia equation. Does that make sense?
yeah.
Is that what you did?
Yes.
Oh, okay.
I'm not sure if it exactly that way, but it got the same answer.
Okay, sweet.
You got the moment of inertia and plug it in.
Okay, what is the tangential acceleration of the point? Yeah, so based on that, that makes like all the rest of my stuff wrong.
So that's true.
Yeah.
32.3.
Yeah, that's what I got.
Okay.
32.3.
Yeah, 32.3.
Yeah.
The acceleration times the radius.
And then 0.8 seconds.
I got 0.817.
So that's the same. That's the same, yeah.
And then
5.
That one.
I had no idea.
I got 3.26 after a lot of equations. Oh wait, that's for B.
that's what I got too.
I got 2.17 for A.
That's what I got too.
Sweet.
Wow.
How'd you guys do that one?
Do you have to rewrite the equation? And then you finally get 1/2 times 8 equals 9.8 times H. And then you divide that by 9.8 times H. You get 2.17 as H.
Okay, that sounds a lot more simpler than I was making it. Yeah. I think like because like the angle doesn't matter, or and so that's where I was kind of stuck on. I was like,
It's hard to know what equations to use and
yeah.
what's important. It's kind of the hard part of all this.
All right, number 6. What is the moment of inertia of an object that rolls without slipping down 2-meter high incline starting from rest and has a final velocity of 6 meters per second? Express the moment of inertia as a multiple of mr squared, where m is the mass of the object and r is its radius.
Got 0.08.
0.0889
Same thing.
mr squared.
Cool. That's totally not what I got.
George, what did you
Hard
get on number
lesson.
6?
Yeah, so I got the same thing, 0.0889 mr squared.
Beautiful. Okay. Number 7. Suppose a child gets off a rotating merry-go-round. Does the angular velocity of the merry-go-round increase, decrease, or remain the same? So for A, he jumps off radially.
It's the same.
Yeah,
That's what I said as well.
it's the same. So for B, he jumps off backwards to land motionless. So I thought it increased. If he jumps straight up and hangs onto the overhead tree branch. I thought it was decreasing.
I wrote down that it's slightly decreased because when he pushes down, that's a force that
Yeah,
slow down just a little bit before he's completely off.
because yeah,
I put 6.
and I could see it also being the same too.
Right? Yeah. There's two.
It's
ways
not
of
gonna
looking
it's not
at
gonna
it.
increase for sure
Definitely not.
because there's no force to add to increase it. But
Depends on how rigid the merry-go-round is.
yeah, exactly.
Like if it's super solid and you push down, it's not gonna do anything. But if it's kind of like flimsy, you know what I
Right.
mean? You push down and it'll kind of. Yeah, I know.
What'd you get for that, George?
For the moment of it, no, for the angular velocity for, are we talking about C?
Yeah.
I said there'd be a slight decrease, right? Because he would when he pushes off, right? He'll create like a counter force. That makes sense, right? Yeah.
So sorry, George. What did you think it was?
So for letter C, when he jumps up and grabs the tree branch, I said that the angular velocity would decrease. Let's go down.
Okay.
I'll go down.
Okay.
Increase.
Yeah.
Okay. So yeah, let's just go with that, I guess. That's
Yeah. And then D, it should decrease because he's jumping off tangentially. So he's opposing. Yeah. So D should decrease. Number 8. Calculate the angular momentum of an ice skater spinning at 6 revolutions given his moment of inertia is 0.4 kilograms per meter second. So I got 0.24 kilograms meter per second squared. Divided by mass. Yes, different answers.
I also got 15.1. I didn't put units on it though. I'm not sure what my units are.
KGM squared.
Yeah. Totally just from the book.
You got yours from the book?
The units, yeah.
Oh.
So what did you get, Lou?
W equals 6 times 2 pi, which equals 37, or in a long number. And then you do 0.400 times that long number. And then you get your 15. That's what you did.
Yeah. That's what I did. George, what was your number 8 answer?
15.08.
Perfect.
Cool. All right. So he reduces his rate of spin by extending his arms and increasing his moment of inertia. Find the value of his moment of inertia if the angular velocity decreases to 1.25.
You got 1.25?
No.
Oh, sorry.
That was just part of the question.
Oh,
Mine's going to be off as well.
That's what I got.
That's what I know. And T is 0.502.
I don't know if the units for that one.
Time.
C is just seconds.
Oh, that one makes sense.
And good on number 9. Did anyone do it?
Nope.
Yeah, I didn't do number 9.
All of us was like, eh.
Nobody did number 9. Okay.
That was the only one I didn't do.
That's okay.
So if I understand it right, is it basically this same method but it's different?
That's what it's saying. Like the question is saying, but there's no like matching.
Okay, so let's just write down some equations, put down an answer so it looks like we tried and get a grade. Just like the one question that just had like a picture that listed a bunch of facts. And
Right?
there's
No
It's like,
question.
no
yes,
question.
yes. This is some information. We like
Sure,
this.
this is the same concept.
Okay.
Is that even a question?
No, this one's a question.
Angular
But
velocity
there's-
to equation.
Oh,
So-
that's
I just don't really understand how it correlates to this because they're asking different things. So this is
Yeah.
asking if this slides towards a motionless stick on friction surface.
So
What are
we
the
could find.
questions?
So the questions are: what is the angular velocity of the two after the collision? What is the kinetic energy before and after the collision? And what is the total linear momentum? That's what it says before and after the collision.
But on this, like, where's the question says so?
That's what
they're
it.
on here.
That's what it's saying. It's
Oh,
just
I gotcha.
it's just
Okay.
repeat these
Gotcha.
questions.
Okay, I understand now.
Yeah. So we have an A, B, and C part.
Yeah. This slides towards a motionless stick on a frictionless surface. What is the angular velocity to after the collision?
Our fun walks us through it.
Wait, so it gives us the answers?
No. It's
It gives us the equation, so.
Oh, wait.
Yeah.
Never mind. I'm looking because like if you keep scrolling down. Never mind.
Are we assuming it's the same rate of velocity?
Well, I guess we could find originally spins. So maybe it's just saying like we're gonna have a different.
So if you look at like the problems online, like the group work, like, and you scroll down to number 9, right? It has that table, and then it has like the coins and stuff. And then you keep reading down. There's like a big yellow box.
Yeah.
Is
So
that?
That's example 10.15 from the book. So it's saying like do the same problem basically, but we're just going to give you different information. Which is like what it says in number 9.
Yeah.
I think the disc has a different velocity.
So we have to figure out what the velocity is using 1,000 rounds per minute at 1.5 centimeter radius.
I think so.
That's where we need to start, because here it gives us the velocity. Here we have RPM.
So if we find, because that'll give us the angular velocity of how fast it's spinning, and then from that we can find the tangential velocity. Or no, we need to. That's not what we're looking for. Just kidding. What's the angular velocity of the two after the collision? So we're just gonna have a different velocity of the disc, and then we can plug it into this. So it's got
I found my textbook solution.
Yeah, because we need to find the circumference of it, and then it's doing 16.6 revolutions per second. You just do the revolutions divided by the circumference to get speed.
Per second? Is that what you're trying to do?
Yeah, so we need to find the speed at which it's.
So it's like 2 pi over 11, and then the conversion time here is 1 minute over 60 seconds.
Little Google calculator says that the linear velocity is 1.57 meters per second. That's worth anything. That's linear velocity.
Which is what we
One
need.
I found.
What did you get?
So it has like, you know how some of them have like answers on the back of the box? And this one has
Oh. So that's
But that still works because we just need to. We're just having a different velocity. So we can just take that velocity and plug it in to here.
V equals 1.5 centimeters per second.
And then you do 0.05 times 1.57 times 1.2 divided by 1.032, which will get that's 0.09 grams per second.
Beautiful.
If you just take this one and swap out the velocities.
Part B.
And then B is 0.5 times 0.05 kilograms times the 1.57 meters per second squared. It's really, really low.
This one has 22. And
Yeah, so that's from the book. It's different.
for this problem, because it has the same RPM. It says repeat example 10.5.
And since these are the answers to it.
Of course.
Well, if that's the answer. It's exactly the same, yeah.
'Cause so there's something different than besides just doing the.
There must be. It must not just be plug and chug.
Yeah.
Let's copy that down, pretend like we know what we're doing, and turn it in.
Who's turning it in?
Either me or you probably.
Okay.
Because we've had the same answers, right?
Yeah.
I can pop that down at phone. I did have one that was a little different on number one though.
Oh.
I had, so for acceleration I had angular acceleration, and then for translational kinetic I had rotational kinetic energy.
That's what I
And you
put
guys
down.
had
It's the same.
the same.
Yeah.
Angular and
Just
I will do that and then send them.
cool. Did you get all that, George?
Yeah.
Or just Whitney's just gonna copy it down and submit it.
Okay.
Yeah. Cool. See you next week.
Yeah.